All right, recording in progress. And share the screen. All right, so we're up to 1.4. Again, there is no 1.5, so maybe I should switch this to 1.6. Okay, so I introduced 1.4. I'll do a lot of problems in 1.4 today. And some of tomorrow, no doubt, and then we'll go on to 1.6 if possible. Okay. So page 28. So we had 1 to 8 all and 9 to 49 odd. Here, right? Let me show you the questions again. 1 to 8. There's that. And whoops. That. And that. And let's see, how high do we have to go? 9, so there we go. Okay. All right, 1 through 8 all. Now you don't have the even answers in the back, so maybe we'll start off with the evens. All right, so about 2, 4, 6, 8, and you should have the answers in the back of the book for 1, 3, 5, and 7. Specify any axis or origin symmetry of the graphs. Okay, number 2, does it have y-axis symmetry? No, it does not. Right? Because otherwise, this piece here would have a graph sort of like that. So no y-axis symmetry, and likewise no x-axis symmetry, because otherwise this thing would have something up over here in the first quadrant, and it doesn't. Okay. However, it does look like you have origin symmetry. Okay, so if I reflect across the origin, there's a corresponding point there, and a point over there, and even the open circle becomes an open circle there. So for number 2, put down origin symmetry. Okay, so number 2 is origin symmetry. That's how you spell it. Okay, number 4. Okay, it does not have y-axis symmetry. The left side is not the mirror image of the right side. It does not have x-axis symmetry. The top is not the mirror image of the bottom. And it does not have origin symmetry either. Otherwise, for instance, this point here would reflect down here, and you'd have another point here, but you don't. Right? So number 4 is none, has no symmetry. So the answer to number 4 is none, N-O-N-E. And while we're at it, let me go the other extreme. Can you tell the answer to number 3? What symmetries does number 3 have? That's all of them, right? You have symmetry with respect to the y-axis. The left and right sides are mirror images of each other. It has symmetry with respect to the x-axis. The top and bottom are mirror images of each other. If I put a mirror right there, the top reflects across the bottom, and vice versa. And you also have origin symmetry. If you take any point and go across the x-axis, you get a corresponding point on the other side, right? Like there goes to there, and there goes to there. So number 3 would be all, A-L-L. So those are the 2 extremes. 3, you have all 3 symmetries, and 4, you have none of them. Okay, 6, can you tell what happens for 6? 6, I'll give you a hint. There's only
origin
type of symmetry. Can you tell which one number 6 would be?
Would it be X?
Y-axis symmetry, right?
6y.
Y-axis symmetry, right?
Yeah.
So there's a mirror image. Doesn't look like you have x-axis symmetry. The top and the bottom don't look like mirror images. And you do not have origin symmetry because let's say if you have this point here, right, the reflection will be down here somewhere, but you don't have a point over there. So number 6, the answer is y-axis symmetry.
Does have has origin symmetry? Number 5.
Number 5 would be origin symmetry. Yes.
Origin symmetry.
Only origin, right?
Yeah.
Okay. And how about number 8?
Origin.
8 looks like origin symmetry. Right. So number 8, put down origin. You do not have y-axis symmetry. The left and right side are not mirror images. You do not have x-axis symmetry. Top and bottom aren't mirror images. But if you reflect across the origin, so let's say that point comes to there, And that point comes to there and so on. So the answer to number 8 is origin symmetry. Okay. So that takes care of that. So 1 through 8 is done. Okay, how about 9 to 49? So how can I possibly do all these? Well, you may need to know what the graph looks like. So part of it might be just graphing it. So discuss any axis intercepts. That means x-intercept, y-intercept, and describe any symmetry. Okay, so how do you do that now? So I'll do a bunch of those right now. Okay. So if they give you an equation, rehashing what we had last time, I'm going to go through this quickly. It should already be in your notes, but you can always look at the video. So for y-axis symmetry, replace x with negative x and see if you get an equivalent equation. For x-axis symmetry, replace y with negative y and see if you get an equivalent equation. For origin symmetry, you replace both of them, x with negative x and y with negative y. And if you get an equivalent equation, you have origin symmetry. Okay, I'll show you how it works because you might be saying right now, I have no idea what you're talking about. Okay, so I'll show you. All right, so number 9, y equals x plus 3. Okay, you might recall for the intercepts back in your algebra 1, x-intercept means plug in y equals 0. Y-intercept means plug in x equals 0. Okay, you can put that in your cheat sheet if you wish. Yeah, put this piece of information. X-intercept means y equals 0. Y-intercept means x equals 0. Okay, maybe I'll illustrate with a quick diagram here in case you're not sure about that. Suppose I make a graph like that. This is the y-intercept. This is the x-intercept. Okay. But at this point, is x equal to 0? No, y is 0. And likewise, at this point, it isn't y that's 0, it's x that's 0, isn't it? Y-intercept, yes. X is 0 and y is whatever. And over here, on the x-intercept, y is 0 and x is whatever. Okay, so to find an x-intercept, you plug in y as 0. Put a 0 right there, a little bit of algebra, x is negative 3. Y-intercept means plug in x equals 0. So x equals 0, y is 3. So negative 3, 0, and 0, comma 3. So those are the intercepts. Okay. Now, how do I find symmetries? So if they give you the picture, it's pretty easy. You can just kind of look at it, right? Where you say, oh yeah, that has y-axis symmetry, all symmetries, no symmetry. But what if it's like this? You don't have the picture. Well, you could draw the picture, but is there a better way than drawing the picture? Because some of these pictures aren't going to be that nice. So here's where we follow this technique. Okay, so I'll show you what I mean. So first, replace x with negative x. So in the original, wherever I see x, change to negative x. So it would look like this, right? Y equals negative x plus 3. Is that equivalent to the original? Does that look the same as that? No, it does not. So they're not equivalent. So I don't have y-axis symmetry. Okay. X with negative x, if you get the same thing back, y-axis symmetry. Okay, and I do it with replace y with negative y. So right here, where I see y, put negative y. Okay, this pen here becomes this pen here, y becomes negative y. Negative y equals x plus 3. Is that equivalent to the original? No, it's not.
No.
That's also not equivalent. And then I do both of them. Replace x with negative x and y with negative y. So that means right here, put negative y. There it is. Right here, put negative x. Okay. And now, is this equivalent to this? The answer is still no. And by the way, you might say, what if I multiply both sides by negative 1 over here? If you did, you have y equals x minus 3. That's not the same as this. Okay. So bottom line, this graph has no symmetries. Okay. And the problem's actually finished, but you can see that easily with a graph, a quickie graph. Remember from your algebra, that's like y equals mx plus b, right? So y equals mx plus b, slope is 1, y-intercept is 3. So a very crude sketch is like that.
So do you have to multiply by -1 on both sides on negative y equals negative x plus 3
Do I have to multiply by -1? I mean,
on both
you could or
sides?
not. I mean, if you can tell right away that that's not going to be equivalent to the original, let's see, right? That's not going to end up looking the same as that.
But is
But
that
yeah,
a
it's
further
not wrong
step
to multiply
to,
by -1.
yeah, so it's a further step to just to confirm?
Correct. Okay, that's actually a good point. I mean, that's normally what you would do to confirm, is this the same as that? Is because this thing has a bunch of negatives, multiply both sides
Yeah.
by -1 and see if you get the same thing, and you don't.
Okay.
If you multiply this by -1, it doesn't look like this. Okay. But anyway, now we know what the graph looks like, right? From algebra 1, slope is 1. The y-intercept, the b is 3. So a rough sketch is like that. And you can see it's not symmetric with respect to the y-axis. It's not symmetric with respect to the x-axis. And it's not symmetric to the origin, because if it were, then if you have this point, you'd have to have another point over here, and you don't. Okay. So no symmetries.
So whenever you multiply, whenever you prove either negative y or negative x, if it's the same by the original equation, that's when there's symmetry, correct?
If you have symmetry, if you get the same equation at the beginning, after you simplify. That's why we say equivalent equation. Okay, I'll show you more examples.
Okay.
Yeah, where it works. Okay. All right, 15, y equals 1 minus x squared. Okay. And by the way, even before we attack this, you should recognize something like this. Okay. Remember, y equals x squared is a parabola, right? Opens up. And remember what happens when you put a negative? Negative x squared, it's not going to open up, it's going to open
Down.
Okay. And then what does that 1 do?
That's
It
one
takes the graph
intercept.
and moves the graph 1 unit up. Right? So crudely, the graph looks something like that. I'm not graphing it exactly, but we know it looks something like this, right? So from the graph, y equals x squared looks like that, right? Negative x squared would go down, and then add 1 means I just pushed it up 1. Okay, it asks for the intercepts. So remember the protocol for intercepts, x-intercept means plug in y equals 0. Y-intercept means plug in x equals 0. You can put that on your cheat sheet, on your formula sheet if you wish, for the test. Okay, so x-intercept, again, look at this picture. X-intercept, y is 0. Y-intercept, x is 0. You can't see that. Okay, so plug in y is 0. 1 minus x squared equals 0. That's going to be plus or minus 1. If you go 0 equals, scratch paper, 0 equals 1 minus x squared, that means x squared equals 1. So by the square root property, x is plus or minus 1. So x-intercept plus or minus 1, 0. And there it is, roughly. Y-intercept, plug in x is 0. Put a 0 right there, y is 1. That must be the vertex over here. Now test for symmetry. Before I go through all this stuff, okay, now we kind of know what the graph is like. So can you look at this graph? It looks like it has what kind of symmetry? Symmetry with respect to the y-axis.
Y, yeah.
How about x-axis? Doesn't look like it, right? And origin, no. If it had origin symmetry, this point here would mean reflecting over here, you have a point over here. So it doesn't look like. So when I run through all this process, right? This x with negative x and y with negative y business, I should come to the conclusion that I only have y-axis symmetry. Okay, so let's see how that works. So I replace x with negative x. So in the original, take a look at this. Replace x with negative x. So it's 1 minus negative x squared. Okay. But what is negative x squared? Negative x times negative x is the same as x squared. So this equation is the same as y equals 1 minus x squared. I do get the equivalent equation back. Okay. So if we get an equivalent equation, over here, if we get an equivalent equation, we have y-axis symmetry. So yes, we have y-axis symmetry. by this analysis. Now, what about the others, which we say no? Replace y with negative y. So right here, make it negative y. So it says negative y equals 1 minus x squared. That's not the same as that, right? So I don't have x-axis symmetry. And I'm not anticipating origin symmetry either. So replace both of them. So origin symmetry, replace x with negative x and y with negative y. Okay, so that means right here put negative y, right here put negative x. So it's going to look like this. Negative y equals 1 minus negative x squared. And just like before, negative x squared is the same as x squared. So it looks like negative y equals 1 minus x squared. But it doesn't matter. That still does not look like that. So I do not have origin symmetry. So by this analysis, I find y-axis symmetry, no x-axis symmetry, and no origin symmetry. And that's borne out by the graph. But I mean, sometimes you can't graph it because it's too difficult. But you got it anyway. Okay. All right, now 19 is very similar to 15. In fact, the only difference, see how it has y equals 1 minus x squared? X equals y squared minus 1. So very similar, kind of. So the algebra is almost the same. X-intercept, plug in y as 0. Put a 0 right there, you get negative 1. So negative 1, 0. Y-intercept, plug in x is 0. Well, the algebra is the same as the previous problem. It's plus or minus 1, right? The algebra is the same as what we did over here, almost. Put a 0 here. 0 equals y squared minus 1. Y is plus or minus 1. Okay, this time I'm not going to bother to graph it. Let's just go straight to the analysis. All right, replace x with negative x. So right here, change it to negative x. Looks like that. Okay, is that the same equation as that? No, no way. Right? That has an x, has a negative x. So I do not have y-axis symmetry. However, if I replace y with negative y, so right there, put negative y, x equals negative y squared plus 1. But what is negative y squared? It's the same thing as y squared. So are these two equivalent? Yes, they are. So my conclusion, I do have x-axis symmetry. And again, if you want to put this entire algorithm on your cheat sheet, you may. And you can put examples. So whatever this thing looks like, it does have x-axis symmetry. And I claim there's no origin symmetry, so how come? So for origin symmetry, replace both x with negative x and y with negative y. So right here, change that to negative x, change that to negative y. It's going to look like this. Okay, that x becomes negative x. That y becomes negative y. And just like the previous equation, we know negative y squared is the same as y squared. So I have negative x equals y squared minus 1. Is that equivalent to this? No, it is not. So once again, I have no origin symmetry. Okay. So that's the way that one works. All right, so moving right along. And yes, you may be wondering, hey, he's doing problems right off the homework. That's right. So every one of these I'm doing is one less you have to do. You know, go back and review it later. And then hopefully that'll show you how to do the rest of the problems that I don't do. Okay. And I want to show you 23, please. Y equals negative x cubed. So replace x with negative x. So right here, change it to parentheses, negative x. So that gets changed to that. So negative x cubed, negative x times negative x times negative x is negative x cubed. But now the negative in front of that makes it just x cubed. All right, so y equals x cubed. Is that equivalent to this? No, it isn't. So I do not have y-axis symmetry. And watch out, if you replace x with negative x, you get something equivalent. It's not x-axis symmetry, it's y-axis symmetry. And likewise, if you replace y with negative y, and you get an equivalent equation, you do not have y-axis symmetry, you actually have x-axis symmetry, right? So look back at the rules that we said here, right? Replace x with negative x, you're testing for y-axis symmetry. And if you replace y with negative y, you're testing for x-axis symmetry. And for origin symmetry, you replace both of them. Okay, so let's see, where were we? Replace y with negative y. So right here, put negative y. It says negative y equals negative x cubed. Now, if you multiply both sides by negative 1, it looks like that. Y equals x cubed. Okay, so is that equivalent to the original? No. So I do not have x-axis symmetry either. However, I claim we have origin symmetry. Because if I replace x with negative x and y with negative y, so that y right there, make it look like that. That x right there, make it negative parentheses negative x. Okay, so that's negative y. And the right-hand side, well, we already worked it out over here. That's going to end up being x cubed, right? Negative x times negative x times negative x is negative x cubed, but the negative in front of the whole thing makes it x cubed. Okay. I claim that is equivalent to this, because if you multiply both sides by negative 1, you do get the original back, y equals negative x cubed. That tells me, so that tells me that we have origin symmetry in the final analysis. Yes, question.
Really quick, for numbers like 23, if they were to ask for the x, like when they ask for the x and y intercept, like it is, you do write down 0, 0, right?
Yeah, I was just
for both of them. Both of them, yeah, okay.
Yeah. All right, so intercepts. If I plug in x is 0, y is 0. If you plug in y is 0, when is this going to be 0, 0? So the only intercept is 0, 0. Okay, and just quickly, you might recall maybe from your earlier work in algebra, x cubed looks like that. Negative x cubed goes like that. And you can see right here, I have symmetry with respect to the origin. If I take this point and reflects it down there, okay, or maybe that point reflects over there. But I do not have either y-axis or x-axis symmetry, it looks like. Okay. All right, then a little bit harder problems like 27, 25, 27. But if you know what the graph looks like, you hopefully can figure it out. 27 will give me this. Now, you can make it a lot easier by factoring. Okay, so factor the top. You know x squared is x times x. What two numbers have a product of 6 and a difference of 1? Well, that would be 3 and 2. And you want to end up with a negative, so negative with the 3, positive with the 2. Multiply back out with FOIL. X squared plus 2x minus 3x is a negative x, and minus 6. And then I notice these cancel out. Okay. So this thing is equivalent to y equals x minus 3 as long as x is not equal to 2. Okay. Very, very strictly speaking, this is not the same as this, because if I only look at this, negative 2 is allowed. If I look at this, negative 2 is not allowed. This was the original equation. So I'm going to say y equals x minus 3, but x equals negative 2 is not allowed. Another way of saying it is this. What happens when you plug in negative 2 here? Get negative 5, right? So I'm going to graph this, except that negative 2, negative 5 is not on the graph. Okay. I can go straight to the graph. What does this thing look like? Y equals mx plus b, right? Slope is 1, y-intercept is
It's a
-3.
linear equation.
It's linear. So the graph looks like this, except there's a hole at -2, -5, because ultimately this is the given equation. So to be really honest with you, in algebra 1, we're kind of sloppy if we just say, oh, this is equal to this. It's not 100% true. This thing is equal to this as long as I don't plug in -2, because -2 is okay here, but -2 is not okay here. So really, really strictly speaking, when I say this equals this, I need to put the caveat that x is not equal to -2, because -2 is allowed here, but -2 is not allowed here. So what happens, you actually have this graph, but there's a hole at -2, -5. So this is what the graph really looks like. It's this straight line, and imagine I just punch a hole. I just punch a hole at -2, -5.
So
Like
one
that.
question, I
Okay.
understand that -2 is not allowed because it becomes undefined. But
Right.
the -5, did you get that one by plugging in -2 on that one?
Correct.
Okay, that's why, got it.
Right. See,
that's
-2,
why.
-5 is allowed here. It's not allowed here. So really, really strictly speaking, in algebra 1, when you were simplifying, you said that's equal to that. That's not quite true. And the reason is because at -2, this is undefined. -2 is defined here. So this
So,
graph looks like this. Okay.
okay, so that means that on the original equation, after let's say you got x² minus x minus 6 over x plus 2. So I understand that when you do -2 at the bottom, it's undefined, but also you plug in then -2 on top, or how do you get the -5?
I plug in -2 here. So I plug in -2 here. I don't want to plug into that. I don't have to anymore. This is the same as this, except for -2.
Oh, okay, okay, that's
Yeah, just
because
plug in here. It's a lot easier than plugging in here.
okay, so you plug in the -2 on x minus 3 times x plus 2.
I just plug in it here. -2 minus 3 is -5. Don't make it more complicated. Just plug into this one.
Okay. Oh, that's right. That's right. Yes, yes, yes. Because we cancel out. Yes, you're right.
Yeah, we cancel it out.
Yeah, yeah, we cancel out. Yeah, yeah, yeah.
Uh-huh.
Got it, got it. So that's
All
how
right.
you find the set of points.
That's right, right.
Got it, got it.
So this is the excluded point. It's not allowed in.
Yes, got it.
All right, the intercepts should be easy. If y is 0, put a 0 right here. X is 3. But if x is 0, y is -3. So 3, 0, 0, -3. So 0, -3, and 3, 0. And now for symmetry, I will only look at this. This is a lot easier than this. So replace x with -x. Y equals -x minus 3. That's not the same thing. So I do not have y-axis symmetry. Replace y with -y, put a -y right there. How does that compare to that? They're not the same. So I do not have x-axis symmetry. If I do both of them, replace x with -x and y with -y, you got a bunch of negatives, negative, negative, negative. -y equals -x minus 3. And you might say, oh, I don't like all those negatives. You can multiply both sides by -1 and they all become positive, right? Makes it look nicer. So -y, change that to -y, change that to -x. Multiply by -1, y equals x plus 3. Is that the same as that? No, it's not. So I do not have origin symmetry. So I have no symmetries. And yeah, you can tell from the graph, right? I don't have any symmetry, right? I don't have y-axis, I don't have x-axis, and I definitely don't have origin symmetry. So at that point would have to give me something over here, and so on. So this has no symmetry. Now, the other extreme, as you might guess, is all symmetries. And what graph did we have before? seemed like it had all symmetries. Would be a circle, right?
Oh, yeah.
Circle, like x squared plus y squared equals 4. That's a circle, center of the origin with a radius of 2. See if I can get this thing focused here. Right. Looks like that. Well, you can just look at the picture and the intercepts are 0, comma, plus or minus 2, and plus or minus 2, 0, right? X and Y intercepts are here, 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 and here. Or you could look at the equation. If I plug in X is 0, right? Y squared is 4, Y is plus or minus 2. I can plug in Y is 0, put a 0 there. X squared equals 4, X is plus or minus 2. Okay, yes, I drew it kind of funny, but it should have all symmetries. If I drew it more accurately, symmetry with respect to the y-axis, x-axis, and origin. Okay. Now, I didn't run through this, but if you do the problem, you should run through it. But you can kind of tell it's going to work. If I replace x with negative x, you get the same thing, right? Because it becomes negative x squared, but negative x squared is the same as x squared. So it's going to be equivalent to the original. And likewise, if I replace y with negative y, put parentheses negative y squared, but negative y squared is the same as y squared. So I get that equivalent. And if I do both of them, well, you know it's going to work, right? Make that negative x squared plus negative y squared. Well, negative x squared is the same as x squared, and negative y squared is the same as y squared. So in that case, I also get the original back. Right? So this is a case of all symmetries. Okay, now I got lazy here. It's not just lazy, I wanted to go on, but you should go through all of this, and I sort of told you what to do. Right? If you replace x with negative x, you end up with the same thing. If you replace y with negative y, you get the same thing. If you do both of them, replace x with negative x and y with negative y, you get the same thing. So here's an example of all symmetries. Okay. All right, then they give you something with absolute value, I guess. Y equals absolute value of x minus 1. Okay, replace x with negative x. Absolute value of negative x. But absolute value of negative x is the same as absolute value of x, isn't it? Because of the bars. So I do get an equivalent equation. So I do have y-axis symmetry. And then if I replace y with negative y, it looks like that. And this equation does not look the same as that. So I do not have x-axis symmetry. And if I replace x with negative x and y with negative y, put a negative y and a negative x. So negative y equals absolute value of negative x minus 1. Once again, absolute value of negative x is the same as absolute value of x. Okay, but is this equation equivalent to that equation? No, it's not. So I do not have origin symmetry. So it looks like I have y-axis symmetry.
So what happens when you multiply on the absolute value when you got negative y, right? And then, so you multiply negative y equals negative absolute value of x minus 1, right?
If you multiply by negative 1, which you don't actually have to do here, but if you did, you'd have y equals negative absolute value of x plus 1. That's not the same as the original.
But I mean, can you multiply after that negative 1?
You can. You can
so when you do
1.
that, you got y?
Y equals negative absolute value of x plus 1. It's not the same as this. So you don't have origin symmetry either. Okay. All right, intercepts, plug in x is 0, y is negative 1. Y is 0. you would add 1. You'd have absolute value of x is 1. That gives me plus or minus 1. So these are my intercepts. Okay, and a real quick graph. Do you remember what absolute value looks like? Absolute value is V-shaped. There's absolute value of x. And then the minus 1 just shoves the graph down 1 unit. So the one that I have in red, that's the actual graph. So intercepts are 0, -1, here it is, plus or minus 1, 0, that's 1 there and 1 there. So the bottom V, it is symmetric with respect to the y-axis. It is not symmetric with respect to the x-axis, and it doesn't have origin symmetry either. Looks like. All right. 39 and 41, I can just talk about, I don't want to graph it in my book. You can if you want, or take a snapshot and do it later. But it says complete the graph so that you have the specified symmetry. X-axis symmetry. So if I were to have x-axis symmetry, I'm not really going to draw it. I'll draw it on a separate sheet of paper. So the x-axis symmetry, you'd have to have something down here.
Yes.
Okay. I know what I'll do. Maybe I'll just write off to the side here. So 39, the graph would have to be something like that. Right? It says complete the graph, so you have the specified symmetry. So x-axis symmetry, it would look like that. Oh, 240, I know it's even. Y-axis symmetry. So complete the graph.
It's 1 to the right,
symmetry. So I have something over here.
like a V.
Right? I get something over here. Like that.
Oh, yeah, yeah. Yeah.
And then origin
Says
symmetry, that might be a little bit tougher, but I'll show you what you can do for that. This is 1, 1, 2, 0. Okay, 1, 1 would come down to -1, -1. 2, 0 would bounce over here to -2, 0. So it ends up like that. So that's how that works. Okay, so it's a little bit tricky. All right, we have some word problems at the end. I'll just do a couple of them maybe, and then otherwise I was going to call it a day. So I'm almost done with 1.4. I'll finish it tomorrow. And then we're going on to 1.6. Again, we're not doing 1.5. It says using technology to graph equations. We're not going to mess around with that. Okay, I can maybe do one of these. 43. Find the distance between the points of intersection of the graphs of y = x² + 1 and y = 2. So how far apart are the points of intersection? So how do you do that? So y = x² + 1 and y = 2. All right. So how do I find out where they touch? Set them equal. So make x² + 1 equal to 2. That's easy. Subtract 1, x² = 1. Do the square root property. X is plus or minus 1. Okay, watch out. When you get something like this, x² = 1, don't just immediately say, oh yeah, square root, answer is 1. No, -1 also works. Right, so the square root property says you have to do the negative also. I mean, -1 clearly works, right? Because what's -1 squared, it's also 1. So I have negative 1, 2, and 1, 2. So how far apart are these points? Well, it's a distance from negative 1 to 1. Right? How far is negative 1 from 1? Well, the distance is 2,
1.
right?
Okay, yeah.
They're 2 units apart. You can graph it if you want to, but you don't really need to, I think. Negative 1, 2, and 1, 2, right? Here's negative 1, 2, 1, 2. They're 2 units apart. So the distance is 2. Okay. All right. So what time is it? We have a few minutes left. If you have any questions. So I'm almost done with 1.4. So let's see. So some word problems at the end, and then I'll get started with 1.6, which is all this stuff. Okay, it looks like a super long assignment, but we'll see when we get there. It's a review of functions. Remember the concept of function? We had functions in trig. Right, so we're getting into functions starting tomorrow. So again, the modified calendar is like this. We're not doing 1.5, so 1.6. So quiz on Friday, and Friday the 3rd of September looks like our first exam. All right.
So there's like 4 sections for quiz 4, second quiz.
Second quiz, right. So 1.3, 1.4, and 1.6 is eligible to be in the quiz.
3, 4, and 6.
Yeah, anything that we do for that week. Okay, and really for these so-called quizzes, you can study, but I don't think you have to study like a regular quiz. It's really more of an assignment because you can use your book, you can use your notes, you can talk to each other, you can, look it up on a computer, on the internet, and so on. So, who am I as a teacher to say you can't study it, right? But you really can get by without studying it too carefully, because once I give it to you, you can use your book and notes, and you don't have to memorize anything, right? And just look everything up.
For the test, for the exam, we need to memorize.
Exam, you don't have to memorize anything that you don't want to. Put it on your cheat sheet, right? So just make up one formula sheet. Good deal. So yeah, you say I can't, I don't remember, I can't stick it in my head. Just put it on your formula sheet.
Oh yeah, the formula sheet can be front and back, right?
Front and back.
Thank you.
One sheet. Standard size 8.5 by 11. Okay, I have to say 8.5 by 11 because otherwise someone's going to say, oh yeah, one sheet, but the sheet is 200 feet by 300 feet or something like that, and it has to be handwritten. You have to write it yourself, not you shrink it down real tight. And you bring a magnifying glass so you can squeeze it. You handwrite it yourself. That's better that way because you learn it better, in my opinion, also. So you can write your own formula sheet, anything you wish to put.
For the ID picture, we need to send you an email, right? With the
email me a picture with your ID and your name, and you can blot out anything else, sensitive information. I just need your name and your picture.
You got my ID, right?
I don't recall, but if I email you back, that's okay. I got it. Or you can send me an email. Again, I can double check that, but yeah. Okay, so again, everybody remember, you need to take a picture of yourself, because class like this, I don't know what everybody looks like. So how do I know it's really you taking a test and not your friend that's a PhD math person, right? So just show me a picture ID before next Friday. Okay. All right. Anything else? Otherwise, we're done. I can't see the chat, so I'm going to stop sharing right now.
So you have in the office hours every day, right?
Monday through Friday from 10:10 to 11. Yeah.
10:10 to 11.
Yeah, and beyond that, by appointment.
Oh, great.
According to the syllabus.
Okay.
Okay. So any other questions, please? All right, that'll do it for today, folks. Okay, so everybody have a good day, and we'll see you next time. Okay, thank you.
Great day.
Have a good day, everybody. Bye.
Bye.
Bye, everyone.